Thank you very much, and welcome to my talk. Today, I would like to introduce to you a new type of attack on an implementation of the Fiat-Shamir transform. This was discovered part of an audit performed together with my colleagues, Maxim and Vesco, from OpenZeppelin. So first, I would like to introduce OpenZeppelin and their work, and also their connection with the ZKP world. OpenZeppelin has been founded in 2015, and by now is a world leader in securing blockchain applications and smart contract systems. As highlights, I can mention their open source contract libraries, which is well known and much used in the industry. It's actually a public good and an industry standard. And together with their Defender developer security platform, they have actually successfully secured thousands of crypto protocols and organizations, among which Ethereum Foundation, Compound, Uniswap, and Matter Labs. More recently, OpenZeppelin has developed a track record in supporting leading protocols from the ZK11 ecosystem. And in particular, they are working to support the settlement layer, the sequencing layer, and the proving layer. The work which I'm about to present today is part of this third layer. And before I give the details of the last challenge attack, I would like to give a bit of historical context. The attack has been discovered as part of a Linea PLONK verifier audit. The initial theoretical concerns we had were regarding the implementation of the underlying Fiat-Shamir transform. It turned out that our concerns were exploitable in practice, which made the discovery a critical vulnerability. This has been promptly communicated to the client, who has swiftly fixed it. However, later on, we have realized that the attack can be generalized, and as such, it can affect any snark implementation which is KZG-based. This means a snark implementation that uses KZG as polynomial commitment scheme. Before I describe to you the details of the last challenge attack, I would like for us to pause and think about the following question. Can you solve this system? It's a linear system of two equations with two unknowns. W1 and W2 are the unknowns. And actually, we should solve the system in the context of elliptic curve points. This means the capital letters represent elliptic curve points. In fact, they are elements in the first source group. And the scalars are actually elements in the corresponding scalar field. As you can imagine, it is quite easy to solve this system, and a solution exists as soon as a couple of simple constraints are met. If you understood this, then you understood actually the core of the last challenge attack. Wait, but there is a bit more. Now let's look at the last challenge attack like in a nutshell. So as I said before, it targets incorrect implementation of the Fiat-Shamir transform in KZG-based snarks. In fact, it targets something more general. It may be applicable to any batched KZG-based protocol in which the Fiat-Shamir transform has not been implemented correctly with respect to what is called the batching challenge. For a concrete setting, the last Fiat-Shamir challenge U, which we have seen on the previous slide, must be computed incorrectly as independent of certain components of the proof or argument pi. The outcome is unfortunately disastrous for the affected verifier, as it allows a malicious prover to compute an argument pi prime for a false statement, while pi prime is accepted with high probability as valid by this affected snark verifier. So in the rest of my talk, I will describe briefly the setting in which this attack was found. I will review the Fiat-Shamir transform, as well as the KZG single and multi-point evaluation scheme. I will give the details of the last challenge attack, and I will highlight some implications and conclusions. For the setting, we have actually discovered the attack as part of a prover, which itself is part of a layer 2 ZK rollup that executes transactions off-chain. In fact, the snark prover has the job of providing a succinct proof for transactions onto L1. Then this proof actually testifies that the transactions have been executed correctly. And then there is an embedded snark verifier on L1 that checks the correctness of this proof. Now, once the correctness of the proof has been testified, the state of L1, the state of L2 onto L1 is updated, as well as the state of L1. And we have to thank my colleague Maxim for this nice graph. And now I would like to briefly review the Fiat-Shamir transform. In fact, the Fiat-Shamir transform is quite handy for providing us with a way to obtain a non-interactive version of protocols from interactive versions. And Fiat-Shamir transform has another nice property that it allows us to prove that the non-interactive versions of the protocols thus obtained are secure in the random oracle model. In practice, the non-interactive prover and the non-interactive verifier have to compute independently the challenges described by the Fiat-Shamir transform using a hash function which is applied to the entire communication transcript up to that point. And as a last reminder for this talk, I would like to present to you in short a summary of the KZG polynomial commitment scheme and its batched version. Don't worry, this is quite important to understand the attack. So I will present to you the interactive version of this polynomial commitment scheme, of this well-known polynomial commitment scheme. And later on, I will talk about the non-interactive version. So KZG assumes assumes two parties, a prover and a verifier, and it also requires a pairing-friendly elliptic curve, and hence an associated secure pairing, a scalar field, two pairing source groups, among other things. And it is actually the KZG polynomial commitment scheme includes three algorithms. A generation algorithm is the first one. This is a multi-party computation which produces a secret X. This is never revealed to any of the parties, but is later used to compute and output a structured reference string. This is a vector of elements in the G1 and G2 source groups. By the way, in the rest of this presentation, I will use a generator notation for G1 and G2 elements. And as a second algorithm, there is the commitment, which simply takes in a polynomial and outputs a G1 element, the respective G1 element. And finally, the more involved third algorithm is the opening procedure, which for a single point KZG polynomial commitment scheme has the following inputs: a set of polynomial commitments, an opening point, and a list of corresponding evaluations. And it follows 3 rounds. In the first round, the KZG verifier simply chooses a uniformly random challenge within the scalar field. In the second round, the prover computes a batching polynomial based on quotient polynomials and on the challenge thus computed in the previous round. It then computes a commitment to this batching polynomial, and this commitment in itself is actually the KZG single point proof. In the final round, the verifier makes further computations related to batching corresponding commitments, and it accepts the KZG proof if a pairing check passes. So this is the KZG polynomial commitment scheme. However, in order to really be able to explain the attack, we need the KZG multi-point evaluation scheme. We will define n as the number of points in which the KZG is being opened. So n has to be greater than or equal than 2. The generation algorithm and the commitment algorithm are the same as on the previous slide. What changes, though, is the third algorithm, namely the opening procedure. And the changes start already from the inputs. We now have vector of sets of commitments, a set of opening points, in particular a set of n opening points, and a corresponding vector of sets of evaluation points. The first round, we already see a change. The verifier does not send only one, but n uniformly random challenges from the scalar field. In the second round, the prover, using these uniformly random challenges, which, by the way, each of them correspond to one opening point. So the prover computes the batching polynomials, one batching polynomial per challenge, and also exactly the same polynomial is computed for one opening point. And for each of these batching polynomials, it computes the corresponding commitment and includes this commitment as part of the batched KZG proof or KZG mass proof. So now the proof actually is a vector of n commitments or n first source group elements. Okay, and the final round, we see already a bigger change from the verifier perspective. The verifier has to choose a random value u. This was not there before. We will see in a minute what it does. We call this challenge the last challenge. Using this challenge and everything else so far, the verifier does further computations with respect to the existing commitments. And finally, it outputs accept if a certain pairing check is correct. It's very important to note that the last challenge U that we have just mentioned on round 3 is only computed and used as such by the verifier, so is never used by the prover. All right, and what is this all about? First of all, I should mention the security of KZG mass in the AGM. This is a protocol which is secure with respect to an AGM adversary. In particular, it has completeness and knowledge soundness. And if you would like to see full details for the proof, please follow those, referenced by Lemma 6 in our latest paper. Now, the attack actually works on an interactive version of the KZG multi-point protocol. So that is obtained regularly using the Fiat-Shamir transform and is secure in the random oracle model. This is something we already know. As a first reminder, all challenges that are computed by both the non-interactive prover and the non-interactive verifier are hashes of the entire communication transcript up to that point in the protocol. And the second reminder is that the last challenge U is actually only computed and only used by the non-interactive verifier. That being said, Now we have to keep in mind the following setting that might actually, and quite often happens in practice. We are interested in reducing computational cost, and this is very important, for example, in the context of blockchain, so much so that we want to even avoid including unnecessary elements in the hashing process. So this bears the following dilemma. Does non-interactive KZG mass protocol still remain secure, in particular knowledge sound, if the non-interactive verifier, actually a variation of it, computes the last challenge U as the hash of only a part of the full transcript, for example, excluding some components of the KZG proof? This is what the last challenge attack is all about. And now, finally, the actual details of the last challenge attack. For this, I need to introduce some notation. I will denote by pi prime KZGN, a malicious non-interactive prover, and I will denote by v prime KZGN, a variation of the non-interactive KZGN verifier, which does the following. Different than this honest verifier, it simply computes U as the hash of the full transcript, but it avoids the first two components of pi KZG. So let's see now the full details of the attack. The first three steps are presented here. The first step is actually a bootstrapping step. The pi prime KZGN, so this is the malicious prover, simulates a single instance, single evaluation point KZG for an arbitrary polynomial evaluated at an arbitrary value. Using the inputs of the KZG pairing check, the malicious prover produces values A and B such that the pairing equation below holds. In the second step, the malicious prover sets the green font variables to their domain respecting values, but to arbitrary such values. Please note that all the values in green are actually all the inputs to the opening procedure. And moreover, the malicious prover sets to arbitrary values within the first source group the elements W3 to Wn corresponding to components of pi KZG. And the prover does all of that in order to come up with a pi prime KZG proof for a false statement. So all it has to do is to compute some values W1 and W2 that make pi prime KZG pass verification. Let's see how it does that. In the third step, using the already set to arbitrary values inputs so far, the prover, the malicious prover, deterministically computes F1 to Fn, following actually the correct logic from round 3 of KZG mass. And in the step 4, this is where the deviation from the Fiat-Shamir transform happens with respect to the verifier, which computes U as the hash of the full transcript, but it excludes the values W1 and W2, which unfortunately allows the prover to exploit and solve the following system of two linear equations with two unknowns, where W1 and W2 are the unknowns, and everything else has been actually computed and fixed. Please note that this is the system that we have talked about before in the beginning of the presentation. And please also note that this system arises from the pairing check that it is included below, and it now becomes apparent where A and B values discovered in the bootstrapping step are used. In the fifth step, the malicious prover fills in the corresponding slots of pi prime KZG with the values W1 and W2 computed in step 4. And finally, in step 6, at this point, the V prime KZGN verifier is doomed, as it accepts the proof pi prime KZG as valid with probability 1. So now let's see a bit the implications of this attack. Imagine a P prime as a malicious snark prover with a P prime KZGN subcomponent. So this malicious snark prover actually can set itself as the owner of all the assets of some L2 layer by simply changing the Merkle root part of, which is part of the public inputs, and thus the malicious snark prover is able to steal users' funds. The conclusion is, in this talk, we have introduced a new type of attack on the Fiat-Shamir transform. This attack exploits the fact that the last challenge defined by the Fiat-Shamir transform was computed incorrectly as independent from parts of the transcript. And this is related but also different from the well-known weak Fiat-Shamir transform attacks, which work when parts of the public inputs are not included in the transcript. The takeaway message here is that the Fiat-Shamir transform must depend on the entire transcript up to that point. And yes, we do have to follow the protocol, even though it looks expensive. So please do mind your Fiat-Shamirs. Thank you.
Thank you very much, Oana. That was great. We have time for a couple questions. So if you have any, please raise your hand, and we will bring you a microphone to ask your question. So go for it. Don't be shy. Yeah.
Can the verifier get by hashing everything but the first point, W1?
Let's get back to the slides. I think it probably does, so that this would be like in a regular KZG, but this is not applicable to a snark then. So we encountered this as an audit for a snark, KZG-based snark, so this is PLONK, and it meant that yeah, we need actually the first two components were not included, but I think so. And then the attack would be on KZG itself, so not on a snark. Yeah.
I guess since we've seen so many of these different Fiat-Shamir attacks, I guess, do you have any learned advice about how to more effectively find and avoid implementing them in the first place?
Probably avoiding is easier. Finding is slightly harder. So avoiding simply means following the protocol. As I said, even though that means probably a bit more costs for the prover and the verifier, and especially for the verifier. By the way, this attack happened not because the people implementing were not aware of possible attacks or the Fiat-Shamir, they simply wanted to reduce cost by any means. So this attack goes to show that trying to cut any cost can be potentially disastrous. We should not cut any cost and reduce security. As to the other question, how to find these attacks, it's actually, yeah, it's not a deterministic process, but there are lots of checks that auditors can do. Basically, they can have a database of possible attacks and start with that and check against that.
Okay, thank you.
if that's it, just looking for the last minute raised hands. Okay, let's. You have maybe one more? We have time for maybe one last. Just wait a second. Can you bring the mic? Can you, please? Can you bring the mic up there? Yeah, right here. It's going to be the last question before the next talk, but yeah, please answer this one.
Yeah, no. I was just thinking, I mean, I don't like it as a solution, as a fix, but if the goal was to save hashes, they could constrain like half of the coordinates of the W1, W2, rather than the full coordinates when doing the hash. Because then when you want to try to find the solution, you have like half of the bits already constrained that you can really mess up with. Maybe. I was just thinking out loud.
I'm not sure what the question is, but I suppose it relates to the representation maybe of W1 and W2.
Yeah, I think the bug arises from the fact that they were trying to save hashes, so they were not constraining the coordinates of W1, W2.
Exactly, yeah.
Instead of hashing all of them, you can hash half of their coordinates, and you save at least one hash that way, but you are constraining half of the... I don't like it as a solution, I was just thinking out loud.
Yeah, I think this would work, and this depends exactly on the representation of W1 and W2. I think they really thought they can get away by not hashing parts of the transcript. So I think the takeaway message is bigger, that we should really include everything in the transcript in whatever form, but it should be included.
Okay.
Okay, if there are no further questions, then.
Yeah, I think we will call it today for now. Thank you very much, Oana.